Hello, everyone. Thanks for coming to Scaling Apps on OKE, to AutoScale or not to AutoScale. My name is Josh Horwitz. I'm a consulting member of technical staff with OCI's Cloud Native Services. And with me, we have Bradley Sargent, who's a senior architect in responses for development. So during this talk, we want to hear from you. Feel free to ask us any questions in the Q&A chat at any time. During that time, we'll have an expert on standby ready to answer all of your questions. And if time allows, we will also answer some questions live at the end of the session during the Q&A. To get started, our agenda for today, we're going to start with an introduction to Kubernetes. We're going to walk through the high-level concepts, and then we're going to touch on scaling Kubernetes. We're going to transition into autoscaling of pods first, and then we're going to go into autoscaling of nodes. We'll follow it up with a demo of pod autoscaling to show you how it looks like in Kubernetes and how you can do a basic example yourself at home. And then we'll go into responses, and Bradley will talk about their journey on OKE and OCI, and their lessons learned, and then we'll transition into the Q&A with time allowed. So to start off, OKE, or OCI's container engine for Kubernetes, is OCI's fully managed enterprise-grade container orchestration platform based around Kubernetes. It's Cloud Native Compute Foundation, or CNCF for short, conformant or compliant, which means that we provide an unmodified upstream Kubernetes experience, which provides cloud portability and assurances that we are following upstream Kubernetes features and functionality and security. As part of OCI, we integrate OKE with a private registry called OCIR. And OKE is available in all OCI commercial regions at go live date, which right now is 21 and counting. Some of the benefits of OKE and OCI are we have high predictable performance from our bare metal instances and virtual machines. We have faster time to market, relying on Kubernetes and cloud native architecture principles. And we have lower costs offered by Kubernetes via bin packing and scheduling enhancements that Kubernetes offers. So some of the key takeaways I'd like everyone to get from this talk are, it's a marathon, not a sprint. So the typical progression for someone starting out with Kubernetes is you're going to use Kubernetes, obviously. You transition into manual scaling. So that means you'll do manual scaling of your pods and your nodes by calling the various APIs. There'll be a reactive experience. So you'll be setting alarms and reacting to those alarms to manually scale. The next path along the journey is you're going to go to autoscale, pod autoscaling potentially, and then node autoscaling. And second takeaway is it's a personalized journey. So this kind of this shows the progression of your journey through scaling, whether it's manual or automated through autoscaling. It doesn't make necessary sense for every single workload to follow the same pattern. Some workloads may use autoscaling and stop at manual. They may go to pod, they may go to node and use all of them. Some workloads inside your same cluster might have a hybrid scenario, and that's all okay. What we're trying to go through here is whether or not you should autoscale and where it makes sense. And so along that journey, it's really up to your business requirements. So to start off, a brief Kubernetes introduction. So one of the most important pieces of Kubernetes is the control plane. The control plane for OKE is a fully managed resource in OKE's service tenancy. We, as OKE, expose to customers the API server of Kubernetes as your entry point into the Kubernetes cluster. We fully manage the API server, etcd, which is the data store, the scheduler, and the various other components of the Kubernetes control plane. The next part of your cluster are the worker nodes. These worker nodes are standard OCI compute instances that run in your tenancy. They're under your control. We provide easy provisioning, automated provisioning. And then after that, you are able to run your workloads in your tenancy and have complete control over those workloads and configuration. To make nodes easy, we have a concept at OKE called node pools. And a node pool is basically a collection of nodes that share the same configuration. So it makes it really easy for you to define a configuration, and that configuration may include the number of nodes, like 3. And if you want to scale, you could change 3 to 6, and we'll provision 3 more nodes with the exact same configuration as your other nodes. So it makes it really easy for you to scale up and down and have repeatable operations against your cluster. And the last but not least, we have pods. Pods are the smallest scalable unit in Kubernetes. They're a collection of one or more containers. A good mapping potentially is that A pod is kind of like a VM. They're not in practical sense, but in abstract sense, they are. So you'd run an application in a pod, and that's your smallest schedulable units. That could be your REST API. It could be a asynchronous worker pulling jobs from a queue. It could be a database potentially. It's really up to you what you want to deploy, but the pod is the smallest unit. And so to recap in this diagram, on the left, we have our managed control plane, and on our right, we have our worker nodes. You'll notice that we have 3 worker nodes across 3 availability domains. We have 81, 82, and 83. And across those workers, we have 6 pods that are distributed evenly for high availability and fault tolerance. So this is kind of the intro to an example that we're going to be referring back to throughout the talk. And so to start off, I want to mention that Kubernetes has built-in topology awareness. So OCI has availability domains and fault domains. These are constructs provided to you to help with high availability and fault tolerance of networking and physical hardware to ensure that one availability domain should not impact another. So you have high availability as a user of OCI. And Kubernetes is fully aware of this. This is part of the integration that we as OKE offer for our Kubernetes users. So you're able to use these constructs to schedule your workloads. So for this example, we are going to assume that these pods are constantly pulling items from OCI streaming, which we add at the bottom left. OCI streaming is a Kafka-compatible queuing system that we're able to stream events through and have our pods consume them and then carry out events. You could think of this as an example would be, we could have items going into the queue, the pods are pulling those items and sending off an email per item. And so this is the example that we're going to be referring back to throughout the talk. And part of, as a business, when we're running these pods and pulling from the queue, we need to ensure that there's always enough pods pulling from the queue so the queue doesn't build up and we're able to send out these emails continuously to our customers and we don't have delay. So, which brings us to our first scaling dimension, pods or applications. At this stage in our cloud native journey, we're still reactive and we're manually scaling our infrastructure as load increases. If the size of our queue is constantly growing for some period of time, then we know we need to scale and add more pods to our cluster, potentially more worker nodes. So after some time, our service became really popular, which is a good problem to have, except the fact that our existing 6 pods can't keep up with the queue. And as we can see, we have an alarm set up through OCI monitoring on the queue size of our streaming queue, and that triggered. So our operator got paged, and in this example, what we need to do now is the operator needs to go add more pods. The way they do this is they would go to Kubernetes API, and they'd be able to scale up an arbitrary number. In this example, we'll scale up 3 pods. So as we can see, the pods have been scheduled evenly across all of the worker nodes that we originally had. So now we have a total of 9 pods. And we're lucky. These pods were able to drain the queue and life continues as normal. The service is back to our SLAs and our customers are receiving emails. Then after maybe some more time passes, we get another alarm because our service keeps growing, our pods can't keep up anymore, so we need to repeat this. But we have a problem this time. The problem is that these worker nodes can only handle 3 pods each. So we don't have a place for these pods to go anymore if we need to scale up more. So in this scenario, the operator not only needs to create more pods, but they also need to create more worker nodes. They're able to do this by calling OKE's API to scale up their worker nodes based on the node pool configuration that we discussed earlier. So now, instead of just adding more pods to our existing worker nodes, we scaled up, added 3 new worker nodes across availability domains, and added those. Kubernetes ran those pods automatically on those worker nodes for us. After a little bit of time, now these pods are able to drain the queue, our alarm clears, our operator can go back to sleep, and the streaming queue goes back to 0. So as part of this example that we'll refer back to as we get into auto-scaling throughout the talk, we successfully added 6 extra pods. We added 3 additional worker nodes spread across availability domains. And we were able to handle continuously the growth of our service as our customer demand grew. How can we accomplish scaling? Well, as we just walked through this example, we have 2 approaches. The one we just did was manual. We're able to scale our pods by calling the Kubernetes API. So you could do this with kubectl, you could do this with Helm, you could do this with various tools. And you're able to just increase the number of pods, and Kubernetes will schedule those across your workloads for you. The second way is scaling your worker nodes. And you're able to do this via OKE's API, which has support for our console, or which is our UI, Terraform, CLI, and SDKs in numerous popular languages, which you can use to scale up your worker nodes. And then on the other end of the spectrum, from manual, we have autoscaling, or automated scaling. And Kubernetes has various forms of this. The first one is we're able to scale pods dynamically based on CPU, memory, and/or custom metrics. Be able to define configurations to tell Kubernetes when it should scale your pods, either vertically or horizontally. In addition to that, Kubernetes has a project called the Cluster Autoscaler, which is the de facto autoscaler of Kubernetes that you're able to use to scale your worker nodes up and down, which we'll get into more later. It's a pretty cool project. So to start our autoscaling journey, let's discuss pod autoscaling. So there's two main ways to autoscale pods. The first is horizontally, which means we're going to modify the number of pods for our application. So we could go from, in our original example, 6 to 9, then to 12 by horizontally scaling our pods. And then additionally, one that we didn't do in our original example is we're able to vertically scale our pods. This means that we can adjust the CPU and memory that we're allocating to a pod. So instead of maybe running 3 on one VM, we could have ran 1 per VM and just scaled it vertically. There's numerous benefits to both of these, especially if you're running in a multi-tenant cluster with other workloads that you want to share your resources with. And so Kubernetes comes built in with the horizontal pod autoscaler, and the vertical pod autoscaler is an optional add-on that OKE supports customers installing today. Both of these autoscalers work by starting out with the user creating an autoscaling rule. Then the vertical or horizontal pod autoscaler use these rules and then query metrics from the Kubernetes control plane. The Kubernetes control plane is a highly extensible piece of software. And one of those extensions is actually the metric server, which is a pluggable interface in Kubernetes. Kubernetes provides a default implementation that you can install, and that implementation provides you with CPU and memory-based autoscaling. But there's other ones that are open source that you could install, like Prometheus, which is a very, very popular metric scraper and querying and alarming tool that's open source. And so you could use the open source Prometheus metric server to not only support CPU and memory, but also custom metrics, which are not provided by the upstream metric server implementation. So after the control plane queries metrics from your metric server of choice, the vertical pod autoscaler then has to make a decision. So it's going to evaluate those metrics based on your rules, and then determine if it needs to scale up, scale down, or do nothing to your pods. It's a little bit more sophisticated than that. It can make sure that it's not changing your pods too often and has some other configuration, but this is the very high level flow of how the autoscaler, whether it's vertical or horizontal, works. So now that we know a little bit about pod autoscaling, let's go back to our original example. Instead of alarming on queue size and being reactive, we're going to add an autoscaling rule that scales the number of pods based on the queue size. So as the queue grows, the autoscaler dynamically changes the number of pods. And as we can see, the queue is at 120. So previously this would have alarmed our operator and woken him up. But now the autoscaler automatically scaled up 3 pods, but unlike before, the queue is not dreaming. So the autoscaler notices that, and it's going to try to scale up another 3 pods. But we run into a unique challenge now. That challenge is before we had an operator manually scaling our pods for us and our worker nodes. So they were able to know that the worker nodes are full and we need more worker nodes for the new pods. Since this is fully automated, the operator's not in the picture. So we have a new problem. We need to add an alarm on pending pods. And so the operator would now come in and autoscale the worker nodes, or not autoscale. They would come in and scale the worker nodes manually to handle the pending pods. OKE actually provides a pending pod metric so that you could add alarms to this. I'm monitoring today to get this next step on your journey for autoscaling or cloud native. So to recap, there's 2 types of autoscaling for pods. You got horizontal which supports CPU, memory, and custom, and provided out of the box. You have Vertical, which modifies the CPU and memory of your pods. It's an optional add-on, and it does not support in-place resizing. So pods get recreated as it needs to be scaled. HPA and VPA could be used together or could be used by themselves. It's really up to your choice. Some applications that you deploy may just use the HPA, they may just use VPA, and other ones could use neither. You have complete flexibility based on your autoscaling rules to pick and choose. And last, the metric server is a pluggable component. So there's numerous open source integrations, like the one from Upstream, Prometheus, and others, and it supports you writing your own custom one if you had the domain to. So the next step on our journey for cloud native and scaling on OKE is node autoscaling. So node autoscaler is a really cool piece of software provided by Upstream, and it's the de facto autoscaling solution that everybody uses. It has two functions. It adds nodes and removes nodes. It adds nodes when pods are unable to run due to insufficient resources. So that means when, for example, before we had pending pods, the autoscaler would react and add nodes to handle those pods. It would ensure the nodes that they're adding have adequate resources for those pods that they're requesting. So you're not just getting a node that the pod can't run on and wasting your time. Also, it removes nodes safely when they're underutilized for an extended period of time and when the pod can run other nodes. The Cluster Autoscaler has some pretty advanced heuristics that it's able to determine what's the cheapest node to drain, how do I move these pods around so that they can be run elsewhere, how do I remove this node, and it supports numerous strategies for this. So the default one is random, where you'll just randomly pick, this is the default, and particularly useful if you don't have different node pools that you need to scale differently. For example, GPU versus non-GPU node pools. It has most pods, which would select the node pool that would be able to schedule the most pods when scaling up. That way you're not doing scaling operations very frequently. It has least waste, which selects the node pool that will have the least idle CPU after scale up. It is aware of price, so we could select the node pool that will cost the least and at the same time be able to run your workloads. And last but not least, there's priority, which selects the node pool that has the highest priority assigned by the user. So now let's go back to our queuing example and look how autoscaling would come into the picture. So if you recall, the horizontal pod autoscaler added 6 new pods, but the first 3 pods were unable to drain the queue. So the autoscaler added another 3, but they have nowhere to run because these worker nodes are full. So what would happen now is the cluster autoscaler would notice that there's pending pods and react by scaling up the nodes across availability domains, because that's what we want here, to handle scheduling those pods. So after the autoscaler does that, our infrastructure would turn into this where we have 3 new workers and 3 pods running. And eventually the queue would drain back to 0. And in this scenario, no operator needed to get paged because the system was able to dynamically respond to the demand of the system. Where an operator would potentially want to get paged is if, say, we didn't have capacity or there was an issue scaling up, the operator could be aware if the queue kept growing or we didn't have enough demand, because part of autoscaling is also you putting bounds on what you want to autoscale. So if you want a maximum of 6 nodes and then you want to get paged after that, you have the complete flexibility to do so. The autoscaler is not going to, by default, just scale infinitely and spend a lot of money. It's you define the criteria that it's able to scale. So to recap, the journey we went on started with, I guess, first using Kubernetes, but mainly manual scaling. So we are reactive in our journey here, where we are responding to demand of our service to increase the number of pods and potentially increase the number of worker nodes to handle the increase in load. Next in our journey was pod autoscaling, where now we allow Kubernetes to dynamically change the number of pods that we have in our cluster. And finally, we have node autoscaling, which is Kubernetes is now able to work in conjunction with the pod autoscalers to scale up and down the number of nodes in our cluster so we can run our workloads. And the journey is going to be highly personalized to your requirements. So it may make sense to stick with manual scaling and improve your automation around manual scaling. You may want to autoscale pods, but not nodes, or you may want all of it. You may want to autoscale pods and workers and not have to deal with it yourself. In the end, you should do what makes sense for your requirements and business needs and where you are along your journey. So now we have a demo. For this demo, we are going to look at the horizontal pod autoscaler. And so on the left, what we have is we have a terminal. And so what I'm going to be doing is I'm going to be creating an HPA, or a horizontal pod autoscaler rule config, that allows us to autoscale our PHP Apache deployment from 1 to 10 max. So our minimum and our default is going to be 1 pod. We're going to allow the cluster to scale up to a maximum of 10. And we're going to trigger this when the CPU percentage across our pods hits 50%. So I created that autoscaling rule, which I could view by running git horizontal pod autoscaling. And what we'll notice is right now it's unknown. So the autoscaler hasn't run this rule yet to determine that it's 0%. We give it a few seconds, it will go to 0%. But in addition to that, we can actually see the configuration. We can see that we have 1 pod, 1 mid pod, and we have 10 max pods. And actually, I know it says 0. If we run it again, it should be updated. So actually, now that it's updated, we can see that it's 0 out of 50. We have 1 pod, 1 min, 10 max, and we have 1 current replica, which is what we expect. So what we're going to do now, in our other terminal, is we're going to run a load generating tool. So in order to do that, so basically what I'm going to do is I'm running a loop that curls our PHP Apache to generate load. And we'll start seeing a bunch of OKs outputted, which means requests are making it through. And so now what we can do while we wait, I'll just show you the UI view of this, which is the Kubernetes dashboard. It takes about 1.5 minutes or a minute for the autoscaler to kind of pick up and notice. And so we'll jump over here. And so the dashboard is a pretty cool project that allows you to hop around your Kubernetes cluster and have a UI view of your cluster. So as we can see here, our PHP deployment that we have that we're load testing is currently sitting around 0.001 cores. And actually, what's kind of cool is we were just able to notice in live time that the PHP deployment actually scaled from 1 to 4. So this is really interesting because this is the horizontal pod autoscaler, and actually now we're at 5. Reacting to our load test. We can actually see these events down here. We can see that the HPA, the horizontal pod autoscaler, set a new size of 4. And the reason was CPU resource utilization was above target. And we can actually see the same thing for 5 down here. We scaled up to 5. And so what we can notice now is after I stop our scaling, if we give it a little bit of time, this deployment would actually go back to 0. So go back. Actually go here and PHPA. We'll watch it this way this time. So actually, you can notice the target is at 36 out of 50%. So we're actually below target. And so what's going to happen is the HPA is going to scale down our workloads. So we'll just give that a couple seconds to run. While we're doing that, this takes a minute of time. It was fast before. So let's watch it. When you add the -w flag, it does a watch. So let's let it kick in. So one thing to call out is you're able to tune actually how quick this behaves or how fast that it scales down. So we might actually be running into the it does a delay. So it's not going to scale up and scale down immediately, causing a lot of spikes. It actually waits a little bit to scale down. So actually at this point, HPA is updated to 0. We're still at 5 replicas. And the reason that it's not scaling down is because it did it so fast that we hit the back off so that we're not just constantly scaling up and down our workloads. So we will actually jump back in from our demo to discuss responses. So Brad, if you want to take over.
Hi, I'm Brad Sargent. I'm Chief Architect of Responses. Responses is a cross-channel SaaS product. It's part of the Oracle CX Marketing Suite of applications. Response has been around for 20 years and just became part of the Oracle family of CX marketing applications in 2014. And a couple of years ago, we started moving on to OCI. Before that, we'd always built our own data centers from scratch. And so we had a lot of experience with building custom data centers and all the networking and all that stuff that's involved with that process. Moving to OCI, I should say we'd already converted to Docker about 4 years ago and running our own Docker hosts in our custom data centers. So in the move to OCI, it made a lot of sense to go into OKE. OKE went into limited availability in April of 2018, and we were active that week from the very beginning. I would just mention that we use OKE for all aspects, for dev, for testing, for staging, and production workloads. We have, like I said, we had a lot of experience building custom data centers, and it takes months and months and months to build out just a single deployment of responses. With OKE, it just really simplifies that process. Kubernetes simplifies it, and then OKE makes it easier to run Kubernetes. Responses has perhaps 50 different types of containers. Some of these containers are really complex. There's a lot of shared state. So that brought us to a decision to take an alternate path to scaling. In our legacy data centers, we would scale out our installations for a long period of time, and they would get more and more complex. What we decided to do was to build what we call a micropod. That's not a Kubernetes pod, but a micropod is a responses deployment, unit deployment. And that has all of the different applications that are required. And in the center of it is an Oracle database. The Oracle database for responses is that which determines how many accounts can go into an installation. So what we've done is we've realized that for us and the complexity and the interrelationship of all these different types of applications, it was easier for us to not auto-scale initially, but instead to define everything around a micropod. And then when the metrics showed us that the pod was getting full, usually because the database capacity is growing, you're reaching that, we would build another micropod and then another micropod. And so that way we're scaling by actually having different installations. And each time, each micropod will have its own database and a whole set of services. In that process, what we found is that it's really important to be able to automate the process for migrating an account to another micropod. And so that's a big part of, and I'll talk more about that in a second. Some of the applications, however, that we have a variety of CPU demands over time. And for those, we're beginning to realize now that autoscaling really would be valuable for those. We don't really want to use horizontal autoscaling because of the impact on our internal configurations. They have shared caches. They have shared a lot of shared infrastructure, and if you add additional pods automatically, you have to change the configurations of the application configuration. So rather than that, the vertical autoscaling makes a lot of sense. So we're looking at that. I just wanted to put in a plug for that. What we have to do now is come up with a static sizing of each of those containers. And that means, for example, our personalization container mostly will run at like 25% utilization. But maybe once a week or once every other week, there'll be a lot of traffic and it goes up to 100%. All of that extra capacity is mostly not used when you don't have autoscaling. So we're working now to add vertical autoscaling just for those applications that have that kind of change over time, so that we can get more efficiency in the way we run our applications. One thing I wanted to mention is that automation is really important for this process. What I described in terms of having a multiple micropods, you have to automate the spinning up those micropods. It now takes us 2 weeks to deploy a micropod, whereas it used to take us months and months to do that. Without the automation that OKE and OCI provide, it wouldn't be possible. So basically, the point I'm making is that you really need to focus on automation across the board. That means automation not only of, like I said, migrating accounts, but also automating deployment, automating rolling upgrades, automating upgrades of the OKE worker nodes themselves. Automation is really key for making all this work. So that's the main message that I wanted to give. Now I think we're going to go into questions.
So the first one that we have is, why would you use pod autoscaling without node autoscaling? So pod autoscaling is a very useful feature, especially if you already have a cluster with quite a bit of extra capacity. So for example, if you're running a multi-tenant cluster where you have numerous teams using capacity, you don't necessarily always need to add more nodes if you have a lot of spare capacity, like in a development environment. So pod autoscaling is useful when you run bursty workloads, like potentially a big data processing job or a cron job, for example. And then pod autoscaling can come in and help you scale out those big data jobs, or help you scale out your API to handle very sudden bursts on existing capacity without having to scale your nodes. It also helps you respond quicker. So having a little bit of extra capacity to autoscale your pods will always be a little faster than scaling out nodes, which requires provisioning brand new compute and setting that up. So it's typically way more common from what I've seen to use pod autoscaling without node autoscaling. But if you're going to use node autoscaling, you're using both of them together. So the next question is, what's the most popular metric server implementation? So the two that I've seen are the ones that I actually mentioned in this talk. So the first one is the open source upstream supported metric server. This is a basic metric server that implements CPU and memory. That is actually what was powering the Kubernetes dashboard that we saw and the HPA from the demo. The next most popular one is the Prometheus. Prometheus is one of the most common tooling I've seen in the cloud native ecosystem. It's one of the CNCF projects. And most metrics exposed by Kubernetes are in Prometheus format. And so that one's growing in popularity. So customers can use the same metrics provider, Prometheus, that they're using to monitor their systems to use to autoscale and support custom metrics. So what type of applications would you not want to autoscale? It's a very interesting question. So it depends on the type of scaling. So what we've noticed, especially with node scaling, like I mentioned, node scaling is a little bit slower because you have to provision compute. Containers are really fast. Instances and provisioning them is quite a bit slower. It can take an order of magnitude of minutes. And so in those scenarios, you might not want to node autoscale a application that's in the customer's path, where they would be unresponsive for those couple minutes and have to wait. So what we've seen is applications that maybe are directly in the customer's path, you want to have a little bit of extra capacity provision to handle those and not necessarily always rely on autoscaling, because then your customer experience will be better and faster.
Another example where autoscaling maybe an issue, like I mentioned in the talk, is horizontal autoscaling. If you have an application that doesn't have elasticity built into its configuration, and it is sensitive to the number of nodes, maybe because it uses connection pools, and if you double the number of containers, then you have twice the connection pools, and that may need to be reconfigured. And if you don't have elasticity in the application, then that isn't going to work so well.
And our next question is, what are the trade-offs of using HPA, horizontal pod autoscaling, versus vertical pod autoscaling? When would you want to use one versus the other?
Well, I guess we talked about that to some extent. Like I just mentioned, the problem with elasticity of the configurations with regards to HPA. And I also mentioned it in my talk, while we're looking at VPA for that reason. So that's something that affected me. On the other hand, if you can do horizontal scaling, then it gives you more overall capacity, because there's a limit to what you can scale vertically depending upon your node capacity. So there's built-in limits with vertical scaling. Also, it's an optional add-on. And I'm not sure, maybe you can help me with this, Josh. I don't think, I think with VPA, you can work off metrics for CPU and memory, but can you have custom metrics as well for VPA or not?
I think that is a new addition, yes.
Okay, all right, so that's not an issue. Anyway, those are the points that come to my mind.
So our next question is, when using VPA, what happens in the container if the container exceeds the capacity of the host it's currently running on? Is it automatically moved to another host with more available resources?
You want to take that one, Josh?
Yeah, sure. So pods in Kubernetes are immutable. Actually, there's only a couple things that you can update on a pod. One of them is the image, and the other one is like labels, like metadata. And so in order to update the resources of a pod, it actually has to get recreated. So in that scenario, what would happen is a new pod would get created with more resources. The scheduler would then pick a new node for it to be placed on. It could be the same node if it worked out, or the scheduler could pick a completely different node with available capacity. It has to re-go through that whole entire flow. So the next question is
responses question.
Yeah, you can take this one.
Okay, responses. The question is, responses convert its applications to containers, were VMs considered, and what are the trade-offs? So we actually, I mentioned that 4 years ago we started moving to Docker. 5 years ago we were realizing we needed to be able to run on the large Oracle hardware. Before, we always had a single bare metal server for each of our applications, and we first looked at VMs. And we had maybe 15% of our applications that, when we did all of our testing and our evaluation, did not run well on VMs for performance reasons. They need low latency and those issues. Plus, some of them needed to store persistent data, application data locally for, and we were basically told with the VMs technology we were using at that time that was not a good idea, because when you upgraded the version of the VM hypervisor, that you could lose that data. That may not always be true for all hypervisors, but that was a concern for us. So we started just working on Docker containers for those 15% of the applications that needed that performance. And once we got up to speed on that and we tested it, all the operations people said, let's just do everything in Docker. It turned out to be a lot easier, because all of your software upgrades and everything are all based in the container. It was much easier than managing it with VMs. So it's a little bit more to get all these applications, including legacy applications, running in containers. We did accomplish that, and it was worth the effort overall. So that's how we ended up getting to where we are.